Okay, so in this video we're going to talk about the transition state theory. Now, this theory is very important in pericyclic reactions. I will explain to you why. If we consider a particular pericyclic reaction, the reaction can happen in either in two pathways, right? The one pathway could be the photochemical pathway, and the other one could be the thermal pathway. Right, so either case, right, if our reaction is going through the photochemical pathway, the thermal pathway is infeasible. So let me explain to you that facts using a energy diagram. So if I draw an energy diagram for a specific pericyclic reaction, it would be like this. So this is the energy. Now here we have the initial products, and here we have the energy. This is the thermal pathway, right? This is the energy variation for the thermal pathway. Now this is the energy variation for the photochemical pathway. I hope you can see the difference, right? In photochemical pathway, you can see the activation energy barrier is relatively low compared to the thermal pathway, which means in this scenario, your pericyclic reaction goes through the photochemical pathway. Photochemical pathway is feasible and the thermal pathway is infeasible. So we call that thermal pathway is forbidden. This is the forbidden pathway. This is feasible because it has relatively lower activation barrier. Now, if your pericyclic reaction goes through the thermal pathway, which means the energy diagram would more like this. So your photochemical pathway, like your energy related to the photochemical pathway, has relatively higher activation barrier. Right, this photochemical pathway, this is the energy diagram related to the photochemical pathway. This has relatively higher activation barrier compared to the thermal energy. So this is the thermal energy. So in this case, you will see that the activation energy barrier related to the thermal pathway is relatively smaller. So your reaction undergoes through the thermal pathway. So we call this thermal pathway, like, okay, these thermal conditions are feasible and the photochemical pathway is forbidden in this case, right? So these are the two scenarios. Now you have to understand a given reaction, a given pericyclic reaction under certain conditions cannot undergo on same pathways, right? I mean, like, one particular pericyclic reaction, right, in a given conditions cannot go on both thermal and photochemical pathways. It can either go from photochemical pathway or from the thermal pathway. That's the case. Like, there should be a specific reaction, right? Specific pericyclic reactions under specific conditions. So under this condition, right, specific pericyclic reactions under specific conditions, your reaction must either go from photochemical pathway or thermal pathway. It cannot go on both. That's very important. So now what we are going to talk about in this particular video is how to determine whether a reaction is feasible on photochemical pathway or thermal pathway. So we use this transition state theory to determine this feasibility. Now I will explain to you how we do this based on an example, right? First, let's consider reaction. I will consider a simple reaction like this, right? So here we have this compound. So the ring is going to be open like this. So this is a very familiar reaction, right? This is the pericyclic reaction which we are going to talk about. So I'm going to give you the specific steps for it, and we are going to see how we are going to arrive on our answer step by step. Okay, so the step number 1, right? Step number 1, you have to draw the orbital structure, right, of the transition state, which means it's like this. So if I draw the orbitals which involves in the bond breaking and bond forming, you will see these pericyclic reactions are mostly based on the p orbitals and the sp2 orbitals. So we have to draw those orbitals here, this one, and we have the 2 orbitals like this. Okay, now in this case you will see there are only p orbitals. Now the transition state, right, the transition state is like this. So this bond is almost broken and the new bonds are almost formed. So I will draw the bonds which are going to break in red color and bonds which are going to form in blue color. Okay, yeah, I will draw it like this so we can have it more clearly. Now here the red color means, this red color means bonds which are going to break. The blue color means, the blue color relationships means the bonds which are going to form. The thing is, this is the transition state. So either of these bonds, right, either of these bond types, the bonds which are going to break and bonds are which are going to form, are not at the 100%, right? So this bond, this particular bond is not fully broken, right? It's still there, but it's going to be broken soon. This blue color bond, it's not formed, right? It's going to be formed in near future. So that's what the transition state means. So all the connections are still forming and still breaking. So the first step of our process to determine in which pathway this particular pericyclic reactions undergo, we have to draw the transition state. So we call these orbitals, which are interacting with our bonds as basis set of orbitals. Right, these orbitals, these are basis sets for our transition state. These are the basis sets orbitals of our transition state. So there we have 2 p orbitals and we have 2 hybrid orbitals. Now in the second step, okay, so let me draw that one again. So let me draw the same color, like in here we have the red and blue. Blue color means the bonds which are going to form and the red color means the bonds which are going to break. Now you have to introduce the phase, right? You have to introduce the phase signs, like, but when you do, you need to make sure that you have minimum number of phase inversions. I hope you are familiar with it, right? In our previous video we have done this. You have to assign plus and negative signs for either parts of your orbitals. So we have done this. If you have not our previous video, I will put the link here. you can go through this link and have a good idea about how to put these signs and how to identify these phase inversions, how we can identify it, how we can form it, how we can minimize it, right? We have to a very detailed overview about it. For now I will go through it. Here what I have to do is, now I have to assign a positive and negative signs to either phase, each phase, right? Each phase of these orbitals. Like, but when I'm doing that, I must make sure that I must have minimum phase inversion. So let's see like this. I will put positive sign here. Now this phase here, right, this phase here is connected to here. Now if I am to minimize the phase inversion, I have to make sure this phase must have the same sign. If you remember, if I make this negative, you will see there's a phase inversion. So I will put positive here, which means negative in here and here, and I will put positive here too. As you can see, there's a connection in between these two parts. So by making this positive, I make sure this has no phase inversions. And here also I will make this positive, and here negative, and here negative, right? So here I have no phase inversion. I have no phase inversions in our compound. So phase inversions are 0. But in this case, like I have told you in our previous video that the assigning signs to each phase of a particular orbital is all on you, right? You can put negative or positive signs anywhere you want. Like as an example, let's say you want to put negative sign here. Okay, you have put negative sign here and you have the positive sign here. Now in that case, you will see there's a phase inversion here and there's another phase inversion here. Other two bonds are okay, right? Other two interactions are here. Positive, positive, no phase inversion. Positive, positive, no phase inversion. We have two phase inversion. So in this case, we have two phase inversion. If you remember, if you have two phase inversion, which means this is an even number. If you have even number of phase inversion, you can reduce it to 0. So you will see, if you interchange these two signs, you can make it to 0. So both these cases, if you manage to make your transient state a 0 phase inversions, or you manage to make it to even number of phase inversion, you are on the same boat. So you don't have to be afraid. So in this case, we call this system an Huckel system, right? We call this an Huckel system. Now in the case of, like, let's say you can't make your whole interactions a 0 phase inversion, so make it even number. You have phase inversions of, you have 1 phase inversion or 3. So this is not even, right? This is an odd number. So in this case, you can't make these phase inversions to 0. You can't make it. So in this case, we call this as a not an Huckel system. This is not an Huckel system. We call as Mobius system. We call this Mobius system. You need to remember these small rules when you apply this theory. So let me go through it again. First thing you have to do is you have to draw the transient state with the interactions. Transient state, you have to clearly draw the bonds which are going to break and bonds which are going to form. Both of these type interactions are very essential to our future paths. So then you have to assign the phases, like positive and negative signs to each phase of the orbital. After that, you can see where the phase inversion are going to occur. So you have to make sure you make your phase inversion into a minimum amount by interchanging the positive and negative signs in a particular orbit, like this. But in the case, if you have even number of phase inversions or 0, which means you are on a Huckel system. If you have phase inversions of odd number, or otherwise you can't make it to 0, you are in a Mobius system. Either way, it's fine. In each system, right? In Huckel system, you have a specific rules, and Mobius system, you have a specific rules. Now in the step 3, right, in step 3 we are going to assign these our transition state, right, whether it's aromatic or not. Right, we are going to assign our transition state whether it's an aromatic or non-aromatic. So if you remember, we have identified whether our system is a Huckel system or a Mobius system in step 2. I hope we are clear up to now. So in step 3, based on our details here, based on our conclusion here, let's say our molecule is a Huckel system. So let me right here, our system is a Huckel system, which means you have no phase inversions. So in that case, right, in that case you must apply 4n plus 2 rule, right, you must apply 4n plus 2 rule if your compound is, if your transition state is aromatic. It's 4n rules that applies when your transition state is non-aromatic. So how we determine these things? Now what you need to do is you need to count the number of electrons that take parts in these interactions. So if you see, there are 2 electrons here and there are 2 electrons here. There are total number of 4 electrons that take parts in these interactions, right, this whole bond breaking and bond forming. So here look at this one, the whole bond breaking and bond forming thing. So this is a bond, right, this is the bond where which are going to break. So this is the place where 2 electrons are positioned. This is the place where 2 electrons are positioned. There are not electrons in here yet. So all this process, right, all these interactions are based on these 2 pairs of electrons. So total 4 electrons are there, right, total 4 electrons are there to interact with each other and form this transition state. So our number of electrons are 4. So according to Huckel's system, our transition state is non-aromatic because it follows the 4n rule. You can't put 4 number of electrons in this system, right? This n is a integer. So it's 1, 2, 3, 4, likewise. So you can't find a n value where this whole 4n plus 2 make a 4. But if you apply n equals 1, this becomes 4, which means your system, your Huckel system is non-aromatic. Now that's the case of Huckel system, right? That's the case of Huckel. Now what if our system is Mobius system? Now if our system is Mobius, then the opposite happens. Here we have the 4n rule for the aromatic systems, 4n plus 2 rule for the non-aromatic systems. If your total number of electrons which take part in the whole interacting thing, right, whole interactions follows the 4n rules, then it's aromatic in the Mobius system. If your total number of electrons which take part in this whole interaction thing is 4n plus 2, it's following 4n plus 2 rule, then it's non-aromatic. So this is very important. This is very important. You have to memorize this rule when it comes to your exam questions. Okay, now we have identified whether our transition state is aromatic or non-aromatic. Okay, now we know our transition state is aromatic or non-aromatic. Now in our final state, right, in our final step, we are going to see the feasibility. I hope it's step 4 here. It's step 4. Now in final step we have 2 pathways, right? If you remember, we have the thermal pathway, we have the photochemical pathway. Now in the thermal path, so sorry about it, let me draw a clear line. Okay, I'm going to divide it again. And in thermal pathway, right? In thermal pathway, let's say you have obtained a transition state in aromatic, right? You have identified that your transition state is aromatic. Then you can say your thermal pathway is allowed, but your photochemical pathway is forbidden. But if you have non-aromatic transition state, then your thermal pathway is forbidden, your photochemical pathway is allowed. So this is the set of rules which we have to follow in our transition state theory. Now here you can see, for our example, right? For our example, if I go through the whole process again, through our example, we have obtained our transition state. And remember, the important thing, you need to draw both the bonds which are going to break and which are going to form in the same transition state. So make sure you can either put the dashed line for the bond breaking or dashed line for the bond forming. Likewise, anything that you can choose anything, right? You can choose any form, but you need to be clear on what bonds are going to break, what bonds are going to form. And the next, you need to assign the signs for each phase of the orbital. Now make sure when you assign the signs, you need to make your phase inversions to minimum amount. Either way, if you have even number of phase inversions or zero phase inversions, which means you are in a Huckel system. If you are in a odd number of phase inversions, which means you are in a Mobius system. Now based on this system, right? Based on this system, you can go forward. So in this case, in our example, we have a Huckel system. So we are going to move forward with the information that we have a Huckel system. So in step 3, what we are going to do is we are going to determine the aromaticity in our transition state, whether it's aromatic or non-aromatic. So we know our transition state is Huckel system. So we have to see in what rule that it follows the number of electrons which involves in the interactions. So you need to calculate the number of electrons which involves in the interaction. So if I go here, you will see there are two bonds which are already in there, right? Here there are two bonds. So I'm sorry, yeah, this is a pi bond, right? Okay, so there are two bonds which are involving in our whole interactions, which means there are 4 electrons. So if I go through that, you will see we have two choices, either 4n plus 2 or 4n. 4 electrons doesn't follow the 4n plus 2 rule, it follows the 4n rule. If you make the n equals 1, then you can obtain 4 in this case, but you can't make 4 in this case. So which means your transition state is non-aromatic. Okay, so we have determined the type of our system, whether it's Huckel or Mobius, and then we have determined the aromaticity. So in our case, it's non-aromatic. Now finally, we are going to use that information, right? We are going to use that information for our feasibility. So our compound is, our transition state is non-aromatic here. Our compound is non-aromatic. So you will see for non-aromatic transition state, the thermal pathway is forbidden. Photochemical pathway is allowed. So our pericyclic reaction, this reaction follows through the photochemical pathway. So we came to that conclusion based on the transition state theory. So I hope you are okay with the whole theory. It's not a big deal. Like, only thing you have to practice with the several examples. So we will do some examples in our next few videos. For now, you need to have a very clear understanding and you need to remember the rule conditions, especially about this, the aromaticity, like in which system we use in which rule, right? and also in this case the feasibility, what are allowed and what are forbidden. You need to be very clear about it. These are very popular questions in your exam paper, so we have to be ready for it. So we will do some questions in our future videos also. For now I will stop here. If you have any problems, please feel free to comment below. I will try my best to answer those questions.